In today's class, we will look into one more classification of signals, that is causal and non-causal signals. This is not casual, this is causal. What do we mean by causal? What do we mean by causal is that it caused something. That means when I give an input, it causes an output. So that is what we call it as a causal and non-causal signal. So this signal will cause something. It's not a casual, so it is causal. Alright, so when do we call a signal to be causal or non-causal? A signal x of t is considered to be causal if it does not exist for negative values of t. That means x of t is equal to 0 for t less than 0. As we know from our understanding, if you take the number scale, so this is our 0 point, this is plus 1, plus 2, etc. up to infinity. This is minus 1, minus 2, minus 3, etc. up to infinity. So we say that the signal is causal if it does not exist for the negative values of t. So t less than 0 means all these values. So if the signal exists for these values, then we say that the signal is causal. That means if we say causal, it should not exist for the negative values of t. It should exist for only the positive values of t. So t is that instant. It can include the current instant or the previous value. So that means a signal is said to be causal signal if it depends on the present and past values. Alright, so what are the past values? T of t minus 1, t minus 2, t minus 3, they are all the past values. What are the future values? T plus 1, t plus 2, t plus 3, etc. They are all the future values. So it should not exist for the future values. So we show here these are the future values. As from the basics of signals and systems, we have understood that a delay in signal, the signal will get shifted to the right of 0, and an advance in signal will get shifted to the left of signals. Therefore, the signal can be delayed, but it cannot be advanced. That is what it says. So that means before giving an input, if it is already predicting the output, such things are called as non-causal. Before causing the input, output is coming. So that is non-causal. So if x of t is equal to 0 for t less than 0, it is a causal system. So this is a causal system or causal signal. And if x of t is not equal to 0 for t less than 0, then we call the signal as a non-causal or anti-causal signal. Alright, so this is the classification of signals in terms of causal and non-causal. Now let us take some examples and find out. So whatever I discussed so far is for the continuous time signal. If you are dealing with the discrete time signal, then we represent it as x of n is equal to 0 for n less than 0. This is causal, and x of n is not equal to 0 for n less than 0. That means for negative values of n, if the signal does not exist, then the signal is a causal signal. But if it exists for negative values of n, then we say that the signal is a non-causal signal. Right? Let us take some signals and analyze and find out whether they are causal or non-causal. First signal, x of t is equal to e power 2t into u of t minus 1. Alright? So if you look at this signal, e power 2t is an exponential signal, and since there is a plus sign here, so this is a growing exponential signal. If it is a minus sign, then it will be a decaying exponential signal. Since this is a positive, so therefore it will be a growing exponential signal. Now we know that when we multiply with unit step function, it ensures that it will start at t equals 0, but since u of t is shifted here by t minus 1, so therefore u of t signal will start at, this is 0 instant, this is time instant 1, so u of t will start from t equals, this is our t axis, so it will start at t equals 1 and continue up to infinity. So when we multiply these two signals, so this will be the resultant. This will be the resultant signal. So this is the signal that we are dealing with. Now, if you look at it, where does the signal start? It starts at t equals 1 and goes on up to infinity. Now, does it exist for negative values of t? No. For minus 1, minus 2, etc., it does not exist. So therefore, this signal is qualified to be a causal signal. It is a causal signal. Right? So we have taken this. Now, if the same signal, if I just put it as t plus 1. So as you know from the basics of signals, so what do you mean by u of t plus 1? The signal u of t starts at t equals minus 1. So where is minus 1? This is t equals minus 1. So the signal starts from here. To just to differentiate, I am drawing the dotted line. This is the original signal. Right? So therefore, if you draw what is x of t, which is equal to e to the power of 2t into u of t plus 1. So this signal, if this is a trace of the signal, so it will be like this. This is the new signal, e power 2t into u of t plus 1. So it is starting at minus 1 and extends up to infinity. So therefore, we have drawn the signal. Now check whether is it causal or non-causal. Does it exist for negative values of t? Yes, it exists for 1, or rather it starts at minus 1. So therefore, the signal is non-causal because it exists for negative values of t. So when do we call a signal to be a causal signal? The signal should exist on the right side of the 0 point, on the number line or the x-axis. If it exists for the left side of the 0 point, then we say the signal is non-causal signal. Alright? Okay, so this is for a continuous time signal we have taken. Now let us take an example of a discrete time signal. X of n is equal to u of n minus 1. U of n minus 1. Alright? So we can see from this, what is the signal x of n? It is a unit step function and it starts at n equals plus 1. So therefore, if you draw this signal, this is at n equals 0, this is at n equals 1, n equals 2, n equals 3, etc. And this is at n equals minus 1, n equals minus 2, n equals minus 3, etc. up to infinity. So therefore, when we say u of n minus 1, it starts at n equals 1 and has a constant amplitude of 1, and since this is a discrete time signal, it exists for only discrete values of n. So therefore, this is our x of n signal. X of n, which is a unit step function, which is starting at n equals plus 1. So here, if you check for different values of n, when we say that the signal is causal, it should not exist for negative values of n. So when we see here itself, we can understand that it does not exist for the negative values of n. Just to be very sure, let us put the values of n in this equation and find out. At n equals minus 1, at n equals minus 1, if you put what is x of minus 1, that is when n has taken the value minus 1, x of minus 1 is minus 1, when n has taken the value minus 1. So wherever n was there, I have replaced it with minus 1. So x of minus 1 is equal to u of minus 1. Minus 1 is how much? Minus 2. So u of minus 2 is 0. You know that u of n is equal to 1 for n greater than or equal to 0. Whatever is the inside the bracket term, it should be 0 or greater than 1. It should not be less than 0. That is what. Now what did we get inside the bracket? We got less than 0. So therefore, the u of n does not exist for that. So therefore, the signal is 0. So therefore, the given signal is a causal signal. Alright. Now for the same problem, if you take x of n equals n plus 2. What do you mean by this? So the signal u of n does not start at n equals 0. It starts at what point? At n equals minus 2. So where is minus 2? This is our minus 2 point. So the signal starts from here and continues up to infinity. So this is what we are drawing. This is what is given in the equation here, or the signal here. So this is our x of n. Now you put different values of n. N equals 1, n equals plus 1, n equals plus 1. So 1 plus 2 is how much? 3. What is u of 3? Is 1, because from the definition of u of n, n should be greater than or equal to 0. So u of 3 will be 1. So it will exist. Now you put negative values of n. N equals minus 1. N equals minus 1. So minus 1 plus 2 is how much? 1. So u of 1 will be 1. So therefore, the signal exists for negative values of n. Next, you put n equals minus 2. When n equals minus 2, I have put minus 2 in position of n. So minus 2 plus 2 is 0. What is u of 0? U of 0 is 1. So therefore, x of minus 2 is equal to 1. So that means the signal exists for two negative values of n. So we say that the signal is non-causal. Even if it exists for one negative value of n, then the signal is non-causal. It should not exist for even one negative value. Then only the signal will be considered to be a causal signal. So this is an important point we need to discuss about the causal and non-causal signals. Alright, next let us look into what are systems, and let us look into the classification of systems. So we can take up more problems and solve this. Okay, let me before concluding, let me take one more example. X of t is equal to cos 2 pi ft. cos 2 pi ft. So this is a periodic signal. It exists for all values of t. So that means it exists for positive values as well as negative values of t. So therefore, is this causal? No. Why? Because it exists for negative values of t also. Now for example, you just check here. What is when t is equal to minus 2? Let us simply check what is the function value. Now has t taken negative values? Yes. I have put t is equal to minus 2. So what is cos of 2 pi f into minus 2? That is cos 4 pi f. Now is the cos 4 pi f 0? No, it is not 0. It gives some value. So therefore, though we have taken the negative values, the signal has not become 0. So therefore, we say that this signal is a non-causal signal. Now for the same signal, if I simply multiply this with u of t, so it's a product signal. I have multiplied the two signals. So first, if I simply draw what is causal, the cos 2 pi ft, so it goes on like this. So it starts from minus infinity and goes on up to plus infinity. That was cos 2 pi ft. Now if I multiply with u of t, it makes sure that the signal does not exist for negative values of t. It starts only at t equals 0 and continues up to infinity. So this is our cos 2 pi ft u of t signal. Now in this, you check whether the signal is existing for negative values of t. Same, let us put at t equals minus 1. At t equals minus 1, x of minus 1 is equal to cos of 2 pi f into minus 1 is minus 2 pi f. Alright, into u of minus 1. So this term is not 0. This term is not 0. But what about this term? U of minus 1 is definitely 0. Why? Because u of t does not exist for negative values of t. So therefore, this is non-zero, this is 0. When you multiply both of this, it is 0. So therefore, we say that the signal is a causal signal, and this is the proof. You put any other negative values, the signal value will be 0. Why? Because you have multiplied with the u of t function. So therefore, this signal is when we multiply with u of t function, the signal becomes causal signal. Otherwise, the simple periodic signal is a non-causal signal. Alright? Now we will go to define what is a system. So basically, we will represent the system in a black box. What is a system? In the first class I have defined it. It will take some input and we call that input as x of t if it is a continuous time system, and does some operation on that and gives the output y of t. So how do we represent here? So we represent this as y of t is equal to some operation called t performed on x of t. Alright, so this is the notation. So what is the system doing? It is doing some operation on the signal x of t and giving the output. It can be any operation. For example, if I simply take y of t is equal to a into x of t, where a is a constant. Now what has happened here? We know x of t is the input, y of t is the output. What happened to x of t? It simply got multiplied by a constant called a. So what is the system doing? It is multiplying the input with a constant a and giving the output. That's all. Alright? Next, if you or this works like an amplifier. If a is greater than 1, it works as an amplifier. It is amplifying the signal a x of t by some value, increasing the amplitude of the signal by some value. Amplifier or a multiplier. Alright? Suppose y of t is equal to integral of x of t d. or x of tau d tau. Simply we will take another example, x of tau d tau. We know x of t as an input, y of t as an output. That is all we know. Now because of this t operation, what has happened? It has become an integral. So what is the operation performed on x of t? It is the integrating function. Okay, so it is the integration operation being performed. So the system is an integrator. It can be a differentiator, amplifier, and so on. Or let me take another example. Y of t is equal to root of x of t. What has happened? You are finding the root of x of t. So therefore here the square root is the operator on the signal x of t. So therefore this is a system. What is the system doing? It is performing a square root operation, or it can be a square operation. X, we normally represent this as x square of t. Y of t is equal to x square of t. We know we have given only x of t as the input. Y of t we know is the output. So what happened to y of t? It became x square of t. That means it is taking the input, squaring it and giving the output. So this we call it as the squaring operator. So therefore these are the different operations by the system. So system can be doing any operations. Alright. So it will take the input, perform some operation on the input signal and give out an output signal. So that is what we call the system. So if it is a discrete time system, we represent the input as y of n and output as y of n. X of n is the input, y of n is the output, and for a discrete time system, the output is represented as y of n is equal to t of x of n. T of x of n. So t is a operator on x of n to get y of n as the output. So this is a simple understanding on what is a system. Alright. Now let us take what are the different classifications of the system. So there are different classifications of the system. The first classification is continuous. As I said, we had already discussed here. It is continuous time system and discrete time system. Discrete time system. What do you mean by a continuous time system? It deals with the continuous time variable and it exists for all values of t, or it exists for many values of t. That means even for fraction values it will exist. When you say discrete time system, it exists for only integer values of t. So that is what is the first classification of the system: continuous time system and discrete time system. Again, these can be memory and memoryless system. Memory systems or memoryless systems. It can be memory systems or memoryless systems. Memory or memoryless. Memory or memoryless system. And we can again classify this as causal and non-causal system. Causal and non-causal systems. Causal and non-causal systems. Next, we can also classify this as linear and non-linear systems. Linear and non-linear systems. We will take each of this and understand what we have already understood. What is a causal and non-causal? We will take each of this and understand. So the next classification of the system is time variant and time invariant system. So if the system is linear, we call it as a linear system, or it can be a non-linear system. So what do you mean by time variant or time invariant? It does not vary with time. It is called as a time invariant. If it varies with time, then it is called as a time variant system. Time variant or time invariant. Time variant or time invariant systems. So these are the different systems, and of course one more classification, and very important classification is whether the system is a stable system or an unstable system, or it is an unstable system. So we will take each of this and understand and classify the systems. Let us take some examples also on each of this and classify them. Okay, so I think we have covered this discrete and continuous time system in good amount. Now let us look into what are memory and memoryless systems. Memory and memoryless. If the system has memory, we call it as memory systems. So this is also called as static or dynamic. If it has memory, we call it as dynamic system. If it is memoryless, we call it as a static system. There are two names for this classification. So they can be memoryless or memory system, or it can also be called as dynamic and static system. So memoryless, static, memory system, dynamic. Now what does this mean? As the name itself says, it should have memory or it should not have memory. So for example, if you are dealing with a continuous time signal, x of t, y of t is equal to x of t minus 1. Alright? So when we say a system is memoryless, we say that the system is memoryless if it depends only on the present value of t for a continuous time signal and not on the past or the past or the future values of t. Now here if you see this at t equals 0, we are calculating y of 0 is equal to what? X of minus 1. What is x of minus 1? It depends on the past value. So therefore, we are talking of 0 and the past value is to the left. So therefore, we are talking of the past value here. So we are talking of 0, but the output depends on the past values. So we say that the system is a memoryless system if the output depends only upon the present value of the input, not on the past or the future values. But in this case, it depends on the past value of the input. So therefore, this is a memory system or it is a dynamic system. Now for the same, let us take another example. For a discrete time signal, y of n is equal to y of n equals 2 into x of n plus 1. Alright? Now we know y of n as the input, x of n as the input and y of n as the output. What has happened? What does the t operator do? It took the signal x of n, multiplied it by an amplitude 2 and it advanced the signal by an amount 1 time unit. Alright, so therefore those are the operations performed by the t operator. So now is this signal or is this system a memory or a memoryless? Now let us put at n equals 0, simply let us take for n equals 0. At n equals 0 means y of 0. y of 0 is equal to 2 into x of 0 plus 1. X of plus 1. So it is not the, I am talking of 0 and plus 1 is ahead of me. So therefore I am talking of a future value. So therefore the system is a memory system. It requires me to store the future value. So therefore the system is a memory system. Let us take another example. Y of continuous time signal. Y of t is equal to cos 2 pi ft into cos of 2 pi ft into u of into x of t. Simply let us take this. Alright. Is this signal or is this system a memory system or a memoryless system? Now what has happened to what did the system do? We gave x of t as an input, we got obtained y of t as the output. What is y of t? Cos 2 pi ft into x of t. That means the input is multiplied by the cosine function or the cos 2 pi ft function. Alright. So therefore, now what is this? At t equals 0, y of 0 is equal to cos of 0 exists and x of 0. So x of t is what we are talking about, the input signal. So x of t. So this is cos 0 and x of 0. At t equals minus 1, y of minus 1 is equal to cos of minus 1. Of course, you multiply all these terms, it will be equal to minus 2 pi f and x of minus 1. Alright. So when we talk of minus 1, in the output, input also is minus 1 only. Input is not some delayed value or a advanced value. So therefore, this system is a memoryless system. It does not contain any past or the future values. So therefore, this system is a memoryless system or a static system. Alright. Now let us take another example. Y of n is equal to x of n square. X of n square. This is a discrete time signal. We know x of n as input, y of n as the output. Now what happened here? What is the operation being performed? The operation is performed on the variable n. N is squared. N is squared in this by the system. The system is performing the squaring operation of n. Alright. Now let us take at n equals 0. At n equals 0. At n equals 0. Y of 0 is equal to what? X of 0. Happy. The system does not depend on any other value. It depends on the current value for this. Okay. Let us take n equals 1. N equals 1, y of 1 is equal to x of 1 square. What is 1 square? Is 1. So therefore, it depends on the present value only. We will say, happily say, it is a memoryless system. Now let us check for another value. At n equals 2. At n equals 2, y of 2 is equal to what? X of 2 square. That is equal to x of 4. We are talking of 2. Output, at the output we are talking of time instant 2, but the input is talking of the time instant 4. 4 is ahead of 2. So that means we are talking of a future value, not the present value. The present value of n is 2. Here, the output is depending upon the future value of the input. It is already predicting, which is not. So therefore, this is a dynamic system. Alright. So we call this as a dynamic system. Similarly, even if you take root n, y of n is equal x of root n. So what is the operation performed? It is performing the square root on the n variable. Alright. Now if you check what is the, whether is this memory or memoryless. At n equals 0, y of 0 is equal to x of 0. It is memoryless for this value. When n equals 1, y of 1 equals x of root 1 is 1 only. Root of 1 is 1 only. So therefore, for this also, at n equals 2, x of root 2. Now you see that root 2 is not a integer value. It is a fraction value. Does a discrete time signal exist for fraction value? No. So therefore, we say that it depends upon the, not on the current value, on the root 2 value. What is root 2? It is less than 2. So it depends upon the past value, not at the exact 2 value. We are talking of the time instant 2. What is root 2? It is less than 2. So therefore, we are talking of the current value of 2, but the output is depending upon some past value of the input which is less than 2. So therefore, the system is a dynamic system. It has memory. Alright. So directly looking at the system, we cannot, sometimes it is not so easy to tell whether it is memory or memoryless. We have to go there, check for few values, and then only confirm whether it is memory or memoryless system. Okay, so the next class, with that we conclude on this topic. Next, let us look into what are causal and non-causal systems. So similar to the signals, here we are dealing with systems, causal and non-causal systems. Causal and non-causal systems. So when do we say a system is a causal system, and when do we say a system is non-causal system? So if for a continuous time system, y of t is equal to t of x of t, and for t less than 0, it is equal to 0. That means when y of t, which is the operation of t on the signal, input signal x of t, it is equal to 0. For t less than 0, then we say that the system is a causal system. That means it should not exist for negative values of t. Otherwise, if it exists for the negative values of t, then it is a non-causal system. So the same understanding from the signals, we are extending it to the system also. Alright, say for example, if I take y of t is equal to e power minus 2t into x of t. Alright, so it is simply depending upon, if you put, it depends on the present value. Alright, if t equals minus 1, minus 1, minus 1. I am just substituting for t. Alright, if t equals 0.1, y of 0.1 e to the power of minus 2.1, x of 0.1. So when we are talking of 0.1, the input also is 0.1 we are talking about, and output also is at the time instant 0.1 only. There is no change in the input and output. So therefore the system is depending only upon the present value of the input. So when we say a system is causal, it should depend upon the present value and the past value or the past values, but not on the future values. As I said, causal system means it should predict what, or it should find out what caused the system. After you give an input only, you will find out what caused the output, isn't it? Without giving the input, you cannot say what caused that output, right? So that is why we call this as a causal. Alright. Next, let us take another example. Y of t is equal to x of t t minus 2, x of t minus 2, y of t is equal to x of t minus 2. So x of t is the input, y of t is the output. What does the t operator do? It just delayed the signal x of t by 2 time units. So we have got x of t as x of t minus 2 by performing the t operation on that. So is this system a causal system or a non-causal system? Put for all values of t and check whether it becomes, does it exist for the negative values of t at t equals minus 1. Alright, at t equals minus 1 and so on. So if you see here, it is the time. Okay, so if you see here, y of t is equal to x of t minus 2, and t minus 2 is a delayed signal, and therefore we say that the system depends only on the present and the past values. So at t equals, let us say at t equals minus 1, at t equals minus 1, y of minus 1 is equal to x of minus 3, minus 1 minus 2 is minus 3. So what is minus 3? If you see the timeline, 0, minus 1, minus 2, minus 3. So when we are talking of minus 1, minus 3 is the past value. What is the future value for this minus 1? It is plus, 0 or plus 1 or plus 2 and so on. Those are the future values. When I am standing here, these are the future values I am looking ahead. Whereas these ones are all the past values. So when I see, they are all the past values. So when I am talking of minus 1, y of minus 1 is equal to x of minus 3. So minus 3 is my past value. Now let me talk of present, the positive values. At t equals plus 1, at t equals plus 1, y of plus 1 is equal to, y of plus 1 is equal to what? X of plus 1 minus 2 is how much? X of minus 1. So minus 1. So when I am talking of plus 1, this is plus 1. Where is the, I am talking in the output at plus 1. But what is the input depending upon, the output is depending upon the past value of the input. Where minus 1 is behind me. I am standing at 1. Minus 1 is behind me. I am talking of the past value. So therefore, this is a past value. So the signal or the system is a causal system because it depends upon the past value of the input and not on the future value of the input. So therefore, the given system is a causal system. But for the same, if you take y of t is equal to x of t plus 2, x of t plus 2, then the system is a non-causal system. Why? Because it depends upon the future value. Simply if I take t is equal to 0, at t is equal to 0, y of 0, I am trying to compute the output at the instant called 0. But what is my input dependent upon? Input is talking about y x of 2. X of 2 is a future value. I am at 0, but we are talking of x of 2, which is a future value. So therefore, this is a non-causal system. So I hope the distinction between causal and non-causal system, you will be able to make it and be able to classify the signals as, the systems as causal and non-causal systems. So with this, we will continue with the next class.